Hello. In this video we're doing chapter 12 on technological progress and growth, and this is our last chapter. What we're going to do in this chapter is relax two assumptions we made in the last chapter to keep things simple. Now we're going to layer these on. It won't be too bad. Is we're going to add both population growth and allow for technological progress. We're interested in explaining what changes and what causes economic growth. And what we learned in the last chapter was although savings can change the level of output per person, the level of the standard of living, it doesn't change the growth rate of the standard of living. It can do so in the short run as we move between steady states, but in the long run, changes in the saving rate don't affect the long-run rate of economic growth. In this chapter, we're going to find out that population growth and technological progress can both affect output growth. If we look at growth per person, it's going to be technological growth that makes all the difference, technological progress. So we're going to find out that technological progress is a key component, key determinant of economic growth. So let's look at how we're going to get technological progress into the production function. So technological progress and the production function. What the book does is notes that we can characterize technological progress in several ways. It can be, first, an increase in output for a given level of capital and labor and other raw materials in a more general production function. So we make more of our resources. Technological progress allows us to get more out of the same input. So for the same quantity of capital, say in dollar terms, and the same amount of labor, number of people, we'll get even more output than we had before. Secondly, it can give us better products, an improvement in quality. It can give us new products. And it can give us more variety. So all of these are ways in which technological progress can happen. And what the book notes is that in each case, what this means in each case, what we're saying, okay, so in each case, consumers essentially receive more what they call services from the goods they consume. To take this a little further, try to make you understand this, they want you to think of output as a set of services, like transportation services and eating, you get fed, and that goods provide. So you can think of technological progress as increasing the level of those services. In any case, whether that makes any sense or not, what we're going to do is something relatively simple. We're going to take the production function we had before. Y was a function of K and N. And we're going to add a third parameter, A. And A captures technological progress. As A goes up, you get more output for a given capital and labor. And so A has a positive sign here. When A goes up, output goes up. Now, so A is the state of technology. For instance, the Cobb-Douglas. Well, let me come back to that in a second. Well, let me come back to the Cobb-Douglas in a second. we're going to write this in a slightly different form, in a little bit more restrictive form. So we're going to use that y equals f of k and the product of an. And what this term is called is effective labor. And we'll explain this a little more in a second here. But it's called effective labor. So it says two things, this form of the production function. One, that technological progress, which is A going up, means you can get the same y for less n. So if I doubled A, I can half n and still get the same amount of output. So what technological progress does in this model, for one, is it reduces the labor requirements. It's labor-saving technology. So you invent a computer or something that a person can use, and one person can then do the job of 3 people. So A goes up by 3 and N goes down by to a third, because it takes a third as many people as before. And the other thing is that technological progress, A going up, leads to an increase in output for the same N. So it makes N more effective. That's where this effective labor comes from. You take N and you sort of multiply it by its productivity, the technology, the effectiveness, and this gives you what's called effective labor. So you take the number of people and you multiply it by this A, and you sort of get their power in the productive process. And so we call it just labor multiplied by its efficiency in this model. Now, we're going to do like we did before and assume constant returns to scale. But let me just show you. In a Cobb-Douglas, essentially what we're saying is that y equals, say, k to the alpha an to the 1 minus alpha, which you could write as a to the 1 minus alpha, k to the alpha, n to the 1 minus alpha. This a is just some constant, and you can see that when a goes up, you need either less capital or less labor to produce the same amount of output. Or if a goes up with those fixed, you get more output with the same inputs. But this is just, you could call this a prime k to the alpha n to the 1 minus alpha. And that's just a standard Cobb-Douglas production function where a is capturing technology for you. But we're not going to use a particular form of this. We're just going to use the general form to work with. So we're going to say, okay, y is some function of capital in a times n. We're going to assume, like we did in the past, constant returns to scale. And so that means we can divide by either one of these. So we're going to say y over an equals f of k over an and 1. And remember, we just write this function as y over an is just some little f of k over an. So we don't have to carry that 1 around. In the well, yeah. So this is our new production function, allowing for technological change, technological progress. If we were to draw a picture of that production function, it would look just like it looked before, except the axes are slightly different. So if we put k over an on this axis, y over an on this axis, and draw this f of k over an, it shows diminishing returns just like before, and so on. And so this is a standard production function that we had before, just the axes are now a little bit different. Last chapter we just had y over n. Essentially a was 1 and never changed. Now we have k over an and y over an, but it's a standard production function. So it shows that as you increase k over an, the effect on output is less and less. So you have diminishing returns to k over an. All right, now we just need to do exactly what we did in the last chapter, figure out what the steady state for capital accumulation is. Then we can draw a graph. It'll be just like the graph in a lot of ways. In the last chapter, it'll just be a slightly more general form. So as before, we're going to let investment equal savings, and savings is going to be little s times y. Y is now a different function than before, but it's the same. So we can say AI over AN equals S over AN equals little s times y over AN. But we know that y over AN from what we just did is f of k over AN. So investment per effective unit of labor, I over AN, is just equal to S over AN equals little s f of k over AN. So that's the amount of investment in the economy. Particular I over AN, investment is equal to this. So keep that in mind. All right? Now we need to find this steady state. So just like before, we want to figure out what the capital accumulation equation is, and then find out what it takes to make capital be stationary. So the question we're asking is, what level of investment is needed to keep investment over effective labor constant? Sorry, capital. Last chapter, we looked at k over n. We used that kt plus 1 over n minus kt over n, that's the change in capital, was equal to sf of k over n minus delta k over n. And this had to be 0 at the steady state. And so that equaled that. This equaled this. But in the last chapter, n was constant and a was 1. It was also constant. Two differences in this chapter. We're going to let n grow, and we have, this is going to be growing instead of a fixed number, and this is going to, technology is going to change. We have technology. So, in the last chapter, what we ended up with was sf of k over n equals delta k over n. And that's what we did in the graph, if you remember. What's going to change here is this is going to have an a in it, k over an, and this term is going to change a little bit, as we'll see. Okay. So that was the last chapter. So we can see what's different. So we want to keep k over an constant. So let, as before, delta equal the depreciation rate. That's the same as what we had before. G of A equal the growth of A, the growth of technological progress. So that's how fast we're progressing technologically. And G of N is the population growth rate. Okay, now note, the growth rate of effective labor, that's A over N. The growth rate of effective labor, A over N, is G of A plus G of N. I don't know if you know that rule or not from algebra, if you remember, but the growth rate of a product is the sum of the growth rates. You can show that with logs. The log of AN is the log of A plus the log of N, and you can use that to find growth rates. I won't go through how that works, but that's how you would prove it. One way to prove it is using logs. But it's true that the percentage change in AN is the percentage change in A plus the percentage change in N. The growth rate is just the percentage change. So this just uses a mathematical fact that the percentage change in X, Y is the percentage change in X plus the percentage change in Y. So the percentage change in AN is percentage change in A, or the growth rate in A, plus the growth rate in N. So here's what we're going to claim. To keep K over AN constant, investment must grow at the following rate. Delta K plus G of A plus G of N times K. Here's why. We want to keep this constant, right? This is the change in investment that's needed. Let me call that the change in capital that's needed. Well, I'll come back to it. It's the change in investment or the change in capital. Either way you want to think about it. But anyway, think about this. Over time, K is going to fall because of depreciation. So if we're going to keep this constant, one thing that has to happen is K has to grow by the rate of depreciation to overcome the amount that's just disappearing due to depreciation. So all this does is make up for depreciation. Now, these two things are also growing by the rate G of A plus G of N. If these are growing, we need K to grow at the same rate, G of A plus G of N, to keep this constant. Say there's no depreciation at all. If K didn't change and A of N doubled because they're growing, then this would fall. So you would need K to double. So K has to grow at the same rate of A over N. So this is the amount that K has to grow in order to overcome the growth rate of A and N, and this is the amount K has to grow for depreciation. So this offsets depreciation, and this offsets growth in A and N. It's actually A times N here. So if those are growing, this has to grow. And if this is falling, it has to grow to make up for the depreciation. So if we were to do what we did in the last chapter, we could say that K t plus 1 over A t plus 1 N t plus 1, these aren't constants anymore, minus kt over at nt is s f, this is investment, right, of kt plus 1 at, sorry, this is at time t, nt, minus this whole thing, minus delta kt over at nt plus g of a plus g of n times KT over AT&T. Your book doesn't write this down because it's a bit complicated. But again, it's just saying that this is investment, and this is the amount the capital stock is sort of falling. K over AN is falling. It falls because these grow, and it falls because this is depreciated. So this is the amount KT is falling. This is the amount KT is increasing, because this is investment. And so if you're increasing K over AN faster than it's falling, you're going to get an increase in the capital stock. This would be positive. If this is less than this, then it's going to fall. So if your investment's less than what's needed to keep this constant, capital is going to fall over time. So the condition for a steady state is that this has to be constant. We want to keep K over AN constant. So a steady state means that this is 0. You might want to write another line. Pause. You know how that works. Okay. So the condition for a steady state, and I'll use stars, is that SF of K over AN star equals what? I can combine these. They have the same multiple here. So it's delta plus GA plus GN times K over AN star. So that's the condition for a steady state right there. This is investment. This is the amount that capital falls. K over AN falls over time. So this is what's required to keep it. That's supposed to be a star. This is what's required for the capital stock to stay constant, for there to be a steady state. Well, that's just like last chapter, except for the A and the GA and GN. So we can draw a picture of this just like we did before. So let's do that next. Keep that equation in mind. You've got it written down there. So now this will be K over AN instead of just K over N. And this will be Y over AN instead of just Y. And we'll have one line on here that's delta plus GA plus GN times K over AN. That's just like last chapter, except for the GA, GN, and the A. It was just delta K over N in the last chapter. We have the production function, F of K over AN. And then we've got, we can take S times that again. We have S F of K over AN. And the equilibrium we just wrote down is where this equals this. SF equals delta plus GA plus GN times that. So this is where they're equal right here. So this is the steady state level of K over AN. We would call it K over AN star. And this would be Y, the steady state level of Y over AN. That's not the standard of living. Y over N is, and we'll come to that in a second. And again, if you're not at this point, there's a natural tendency for you to get there. Suppose we're at this K over AN. If we go up here, this is the amount of investment. So that's K going up. This is the amount that K goes down, K over AN. This is the part that makes K over N fall. This is the amount that it makes it go up. It's a steady state when the fall and the increase are balanced. Here, the fall in K over AN is bigger than the increase. Let me make that arrow over the whole thing. It's not just the K part. So K over AN, if it's falling more than it's increasing, would be falling. Down here, you could do the same thing. Pick a K over AN here. And go up to these 2 points, this one and this one. This is the amount that k over an is falling. This is the amount here that k over an is increasing. So the increase in this case is bigger than the decrease, and k over an would tend to increase. And so over time, we would move to this steady state or this equilibrium value. So that's the equilibrium. So it's just like the last chapter in terms of the logic. We just have a few more terms to worry about, A, GA, and GN. But the mechanics of the model are identical to what we had before. Okay, let me redraw just the equilibrium, and then we can make some points about it. So here's what our model looks like. We have k over an on this axis, y over an on this one. We have delta plus GA plus GN times k over an. Production function, f k over an. Then the investment function, s f k over an. This is our steady state, k over an star. And if we go up and give that to the production function, it gives us y over an star. So here's the question. How fast does y grow? If y over an is constant, and a and n are both growing, what do we know about y? How fast is y growing? So again, a and n are both growing. This is GA. The growth rate of an is GA plus GN. So how fast does y have to grow? It has to grow at exactly the same rate, or this ratio couldn't be constant. So it grows at the same rate as a times n to stay constant, although to keep the ratio constant. You keep the ratio constant. So y grows at rate GA plus GN. Okay? Now I want to ask a different question. How fast does y over an grow? Not an, but n. How fast does the standard of living y over n grow? And we're going to use another fact. The growth rate of x over y equals the growth of x minus the growth of y. And that's just a mathematical fact. So this is just an extension of the growth of xy. It's the growth of x plus the growth of y, except that y has a -1 coefficient on it. See, anyway, this is true. All right? So the growth rate of y over n equals growth of y, which we just argued is GA plus GN over here. Has to be to keep y over an constant, minus the growth rate of n minus g of n. So that tells us something important. This is the result we're after. The growth in the standard of living is what? So that tells us that the growth in the standard of living is just g of a. G of a plus n minus g of n equals g of a. And so once we allow for population growth and a growth in the technological progress, the growth in the standard of living is just g of a. Everything depends upon technological progress. So that's the key result. Growth in developed economies depend mainly upon, we'll talk a little more about this in a bit, the rate of technological progress. Okay, good. And let's just look at, again, the effects of an increase in the savings rate. We're going to get a result much like we got in the last chapter. Just like k over a n y over a n delta plus ga plus gn times k over a n. Have a production function f of k over a n. And you want to leave room to rotate this investment function up, so make it hit relatively low on your line here. Here's S0 f of k over a n. That's initial investment. And so this is our initial steady state, k over a n star. And if I come up to here, I can get my the initial standard of not the standard of living, because I have an A. Standard of living is y over n, but that's the steady state level of output per effective unit of labor is right there. And again, growth of y equals GA plus GN, growth of y over n equals g of a. That hasn't changed. Now let's let S go up to S1 and see what happens. Well, what that will do is it will rotate this investment function up to S1 f of k over a n. That'll give us a new steady state, k over a n star, call it. If we come up to here, we will get a new level of y over a n star. And so it raises output per effective unit of labor. It also could raise y over n. So it raises the level of y over n. We kept A hasn't changed here. What's changed is y. But it doesn't change the growth rate. So that's the main point. The main point is the growth rate depends on GA or GN. It has nothing to do with S. The growth rate of the standard of living has nothing to do with with S. And so although it changes y over AN, just like in the last chapter, for a while this grows a little faster. In the long run, because it has to grow a little faster in the short run to get to the higher level, but in the long run, you don't get any effect on the growth rate. So in the short run, you do get higher growth. It has to grow faster than GA over GN in the short run to get you to a higher level. But in the long run, output doesn't grow by any faster than it did before. It's still going to be equal to the population growth rate plus the growth rate in technology. And the standard of living doesn't change. So once again, a change in S has no effect on the growth rate. All it does is change the level of y over AN. And so it can change the level of y over n, but it can't change the growth rate itself. Now there's one other thing we could talk about. The book doesn't really do this, and I won't spend a lot of time on it. But you could also say, what happens if, what if g of a, g of n, or delta goes up? Just show you quickly how to do that graph. So here's k over a n, y over a n. Start with this line. Let me just call it delta plus ga plus gn 0 times k over a n. One of these is going to increase. It doesn't make any difference which one. Here's production, f of k over a n. Here's saving, s, f, that's a little f, of k over a n. So here's our initial steady state would be this k over a n star. And if we come up to here, we can get y over a n star. Now, if one of those things goes up, delta, GA, or GN, what's the effect going to be? It's going to make this line steeper. So what will happen is this line will rotate upward to delta plus GA plus GN 1 times k over a n. It's a bigger number now. One of these three things went up, or all of them, or some of them, whatever. So in that case, what's going to happen? Well, we're going to get a new equilibrium. It's actually a lower one. So capital accumulation will fall, k over nn star star, and we'll get a new level of y over an as well. Remember, these are the things that make capital go down. They make k over an go down. And so when any one of these things go up, it reduces k over an in the steady state. So it doesn't, unless it's a, remember that y over n grows at g of a. Unless it's g of a that change, it's not going to change the growth rate. If it's g of a that change, it will actually change the growth rate as well. What would happen if g of a went up? You'd grow faster from a lower growth rate. But y over n would grow faster, so eventually you'd end up on a better path than before. But you'd start from a lower point. But anyway, the book doesn't show you this one. I just thought I'd toss that in, because you can also look at those sorts of things as well. All right. Not a lot left. Let's go on. So if technological progress is so important, what determines it? Where does technological progress come from? And so the book has a small section here on the determinants of technological progress. And it depends mostly, if you look at the data, on research and development spending by the government and by firms. And so you basically get infrequent major discoveries that really help you a lot. And so you need to be continuously looking to find those things. R&D, research and development, is about 2 to 3% of GDP in most developed countries. And government policies that reduce this are a bad idea. A lot of times, for instance, we give firms tax breaks for R&D and those sorts of things. But R&D is just fundamentally ideas that must be turned into a profit. Fundamentally, they're ideas that must be turned into a profit. Turned into profit. And that depends upon two things. So it depends upon two things, and I'm going to erase. One, what we call the fertility of research. And that is how well R&D, how fertile it is, spending turns into new ideas and products. Sort of the success rate of your R&D. And that could depend upon how efficient you are at it and where you direct your research and how clever you are and all sorts of things. And secondly, what they call the appropriability. Appropriability. And that is the extent to which firms benefit, this is the basis of patent law, from their own R&D. So if you spend all this time and money developing a new product, and suddenly it's this great new product, and other firms can just copy it, you're not going to be able to recover your investment in the ideas. And so you're not going to want to do the ideas to begin with. And so we give firms patents and use other mechanisms to make sure they have property rights over their own ideas to encourage more R&D. So if you go to all the time and trouble to build an Apple Watch, and then suddenly all these other firms come out with watches that are just identical after they copy yours, they just reverse engineer them, and you have no way of stopping them from doing that. There's very little incentive, and maybe it's a good idea with the Apple Watch, we'll see. There's very little incentive to do that kind of work. Sometimes the second mover also has an advantage. You go to all this time and trouble to build a product and you put it on the market. So it goes, oh, I see, that's a really cool product. I can make these small changes and come out with an even better product, and they correct all the little problems you have. And the second mover in the market often captures more of the market share than the first mover. If they can do that, then there's no incentive for the first mover to go first, and there's no incentive to basically to do the research. And so you need to both encourage R&D that's effective in some way. And so you don't want to have government programs that just have people doing whatever. You want them doing things that are fertile, that turn into new ideas. And when they do that, you want to make sure that they're able to capture the fruits of their own labor. As a last question in here, two more things. Is it true that y over n grows at the rate g of a? And the book uses a table. So it looks at the same four countries as before: France, Japan, I think they're the same that we used before, UK, and US, and then the average. And then on one axis, we have the growth, or one column, in y over n. That's y over n. Growth in y over n from 85 to 2009. And they have some way of measuring the rate of technological progress. That's a hard thing to measure. I'm not sure how confident I am in their numbers, but we'll go with what the book did. So the growth, these are annual growth rates: 1.9% for France, 1.8% for Japan, 2.1% for the UK, 1.9% for the US, with an average of 1.9%. These numbers are 1.6, 2.1, 1.6, and 1.3, not a perfect match, though when you look overall, this comparison here is not too bad. And so it looks like there's a rough equivalence between the rate of technological progress and the rate of growth of y over n, at least when we average over countries. It's not perfect at all when we look here, but it does seem to have some validity, at least across countries. There's other factors that would affect these things too that we haven't accounted for, and so if you were to take those into account, you might even get a better fit. All right. Now, there's two ways that an economy can grow in this model. So we have K over AN. So we're in the last section of the chapter, conclusions, Y over AN. And we have this delta plus GA plus GN, K over AN. F K over AN S0 F over KN. So here's our initial steady state at this Y over AN, say star, K over AN star. One way to grow in the short run is to increase S. So this is this, we've been doing S1 F of K over AN. This should be an A there. AN. We're going to get growth in Y over AN in the short run as we move to this new higher steady state. So we'll have a growth spurt. So one way to grow is to move along the production function. So one, S gives you growth in the short run. And we saw, when we parameterized the model in the last chapter, that short run can be decades. So it's a long period of time, even though we're calling it the short run. In the long run, there's no growth from this, but in the short run, there is. Or secondly, you can have G of A go up. That's the growth of Y over N. So that brings us to a few conclusions. So if you look at developed countries since 1985, so conclusions that we can draw. So we're going back to the facts of growth we started with in chapter, I believe, 10. And we're going to come to some conclusions. One, growth since 1985 seems to be from technological progress. This is capital accumulation, S up. And this is technological progress, rather than capital accumulation, an increase in S. This is in developed countries, okay? And we talked about there's been convergence in growth rates. When we looked at the facts of growth, we know that there was convergence. Convergence in growth rates also appears to be from technological progress, not capital accumulation. France, Japan, and UK were all behind the US in '85. They all had faster rates of technological progress, and that allowed them to catch up. Just go back, you don't remember the catch up, go back and look at the table we put on the board, and it's in the book too, from chapter 10. Now the third thing here, so those are for developed countries. Catch up of poorer countries like China and India, their progress, mainly due to capital accumulation. Though it would be wrong to say technology doesn't play any role. Technology also plays a role. But they rely much more heavily on technological progress over time. So poorer countries are generally poorer because they have a low amount of capital. So part of their catch-up has to be through capital accumulation. So poorer countries tend to grow for two reasons. Capital accumulation is a really important part of the story, but and technological progress also plays a role. But for richer countries, it's almost all due to technological progress. Well, thank you very much. That's it.